Good afternoon, everyone, and welcome to the Introduction to Rigid Flex Materials and Constructions webinar. My name is Ed McMahon, and I'm the CEO of Epec Engineered Technologies. As many of you know, this is our 60th year as a manufacturer and designer of built-to-print electronics. Today, our presenter is Paul Tomei. Paul is the Flex and Rigid Flex product manager here at Epec and has been in the Flex PCB business for well over 20 years. Today, he spends the majority of his time working with our customers, helping them with their Flex and Rigid Flex designs to make them more cost-effective and manufacturable. Our objective today is just to provide as much information as possible and to give folks who are not used to this technology some insight into some of the different materials and constructions that are available. Before I turn it over to Paul, I just want to go over a few technical items before we get started. One, if you have any questions, there's a spot at the bottom of the control panel that will allow you to type in any questions that you may have. If time permits at the end, Paul will attempt to answer as many of those questions that come in as possible. Secondly, we're recording this webinar and we'll be posting it on our website along with all the Q&A that we don't get to during the webinar itself. Once we put it up there in the next few days, we'll email everybody a link to the recording and the Q&A so that you can have that for your reference in the future. And then lastly, we plan on doing this every other month, using it as a mechanism to provide more technical information to all of our customer base. So without further ado, I'll pass it on over to Paul.
Thank you very much, Ed. Good afternoon, everyone, and thank you for joining us today. As Ed mentioned, our topic for our introduction, for our initial webinar, is an introduction to rigid flex materials and constructions. The scope of the subject matter today we're going to start off with a little review of the design evolution of rigid flex and what's transpired over the last arguably 10 to 15 years, how that in turn had an impact on rigid flex reliability, and then we'll start delving into some of the actual materials and construction methods that are used today in a modern rigid flex construction. Arguably, over the past decade or two, there have been some very significant evolutions in the design of a rigid flex. Older designs were typically point-to-point interconnects or very, very simple circuits using PTH connectors and components, and had relatively low layer counts, typically in the 3-4 range. Over the past decade, current designs have now started to utilize the rigid areas as fully capable rigid boards. And in turn, we're pushing the very same limits of complexity and density that we currently encounter in modern printed circuit boards. Fine lines and spacings, high aspect ratio vias, sub 10 thou in diameter, blind and buried vias, substantially higher layer counts, upwards of 12, 18, 20, and higher. We're experiencing much higher operating temperatures, and of course we have to deal with the requirements of RoHS assembly. Advanced designs in turn identified a reliability issue, specifically involving the vias within a design and the formation of copper plating cracks within the via holes themselves. The industry, combined with the IPC Association, expended significant energy to determine the root cause, and it was deemed to be the use of flex circuit adhesives within the rigid areas of the design. Flex circuit adhesives have an extremely high coefficient of thermal expansion in comparison to FR4. Typically, depending on the adhesive type, anywhere from 10 to 20x that of FR4. This in turn places the vias under a significant Z-axis expansion stress when the product itself experiences a thermal cycle. And typical sources of thermal cycles are, first and foremost, row house assembly temperature requirements, potential multiple assembly cycles if the product has components, surface mount components mounted on both sides, and lastly, substantially higher system and component operating temperatures. And this occurrence of plating cracks was confirmed through interconnect stress testing, or otherwise known as IST, and then visually determined through scanning electron microscope imaging. So where does that take us? First, let's take a look at the potential sources of adhesive within a design. And they fall into three groups. The first being the copper-clad flex laminate that's utilized. The second, the method in which the coverlay construction is applied to the design. And lastly, the method in which the rigid layers are in turn bonded to the flex layers. As I previously mentioned, this was a significant concern within the industry, and the manufacturing element, material suppliers, and industry standards organizations worked together to develop the following elements to resolve this issue. The first is the use of adhesiveless-based copper-clad flex laminates. Secondly, the development of a selective coverlay construction that could be applied to the product. And lastly is the bonding of the rigid layers to the flex layers using traditional FR4 prepregs. In this case, a material version that has substantially lower flow, but nevertheless essentially the same material that's used within a rigid board. And IPC 2223, which is the design standard for flexible printed circuit boards, the most recent version, Rev C, which was released in November of 2011, in numerous locations defines the elimination or minimizing of adhesives within the rigid areas, the use of adhesiveless-based substrates, and the use of a selective or partial coverlay construction. So moving forward, let's get into the definition of these different elements so that you can have a better understanding. We'll start off with copper-clad flex laminate constructions. Traditionally, in the beginning of the industry and the beginning of the technology, the only material available was adhesive-based. And this required that the copper itself was attached to the polyimide core, utilizing an adhesive to essentially glue the copper to the polyimide. And the adhesives could be either acrylic, modified epoxy, you can actually get polyimide-based adhesives as well. The industry evolved an adhesiveless material, and through a mechanical or a lamination methodology is now capable of attaching the copper directly to the polyimide core, thus eliminating the adhesives entirely from the material. Benefits and drawbacks: adhesiveless materials, because the adhesives have been removed from the equation, in turn allow thinner constructions, in some cases up to 33% thinner or more. That in turn allows for a more flexible or reliable design to be produced. The material itself has a much higher operating temperature rating, much higher copper peel strengths, and through the elimination of the adhesive has substantially reduced, virtually eliminated the thermal expansion stress that would be applied on vias. Downside, there is a slight, at this point in time, there is a slight material cost issue or increase. The delta between the two materials has dropped considerably over a period of time. Regarding the adhesive-based copper-clad laminates, their primary advantage is a lower cost. Because of their technical limitations, we typically see them applied to flex-only applications that are strict point-to-point interconnects, and through assembly, and usage will experience very limited thermal excursions. So taking the next element of the process is the coverlay construction. And for the most part, up until the last 10 or 15 years, arguably, coverlays, which protect the flexible areas, extended throughout the entire rigid area of the design, which in turn defined that the vias and the PTH holes would be drilled through the coverlay adhesive and in turn exposed to the excessive Z-axis thermal expansion stress that the adhesive would apply. It's poor construction. In the example that we have here, we can identify that there are two coverlay adhesives that any vias or holes would be drilled through. The industry, in turn, to address this issue, evolved what we refer to as a selective coverlay construction. And in turn, the coverlays are restricted to the exposed flexible areas of the design only. They do interface into the rigid areas, but only by a very small amount, typically up to 50 thou. And within this transition area of 50 thou, an effective design will also restrict any PTH or via holes from this area. The rigid layers then are in turn bonded directly to the flex core using a high-temp, no-flow FR4 prepreg. Benefits and drawbacks of this methodology. Again, significantly reduced thermal expansion stress is placed on the vias. As a byproduct of that, the design has a substantially higher operating temperature rating. You have a very high layer-to-layer bond strength. Through the elimination of the adhesives, thinner constructions are then available should the design require it. Downside, again, a slight cost increase, in this case due to the greater number of manufacturing process steps required to manufacture a selective coverlay construction. Benefits and drawbacks of a full coverlay construction. Again, it's primarily a cost issue, with the significant downside being, again, the thermal stress reliability issue. As part of the standard quoting process here at Epec, we do a complete design review of the customer's part as part of our quoting process. And in that design review, we'll take a very close look at the specifications that the customer is requiring, the materials that they're defining, the construction method of the design. We do a full DFM on the Gerber data set. Probably most importantly, we'll have a discussion with the customer as to the application, specifically what their electrical and the mechanical requirements are of the specific design. And we'll then also take a look at the design from a point of view of looking for areas of opportunity in terms of either improving the reliability of the design, improving the functionality, or looking for cost reduction areas. Once we've gone through the design review process, we'll communicate any and all technical items and resolve them, and also discuss the potential areas of opportunity with the customer to see if they can be implemented at that time. Once the design review is completed, we'll then generate the quote. It allows us to generate an accurate quote based on a manufacturable, reliable, cost-effective design, and it will eliminate or substantially minimize any potential technical issues that will need to be addressed after a PO is placed. To summarize all of this, modern IPC standards, specified material and construction methods, have essentially eliminated the via stress issue through the construction of utilizing adhesiveless copper-clad flex cores, selective coverlay constructions, and layer and rigid layer bonding with no-flow prepregs. Unfortunately, in our hands-on experience that we see on a daily basis, many current rigid flex designs do not adequately or correctly define modern IPC specified materials and constructions. So where does that leave us as a supplier? Well, this opens a number of issues that may or may not arise if we receive an incorrect, or if the supply chain receives an incorrect or an inadequate design. We have experienced situations where it allows suppliers to utilize less expensive materials and or constructions, in turn to gain a competitive pricing advantage, potentially at the expense of future reliability issues. Should a reliability issue occur, the customer's recourse is severely limited because essentially the parts are being made to the customer's print. Tends to complicate the quoting process. And a correct quote will require that the proper materials and constructions appear as deviations from the supplied specifications. These deviations in turn may not be fully understood by the customer, which in some cases may result in the rejection of a perfectly viable quote. Definitely creates quoting delays due to the added technical communications required. And in a worst case scenario, some suppliers may in turn not identify these deviations on the quote. The parts are then in turn not built to print, and potentially an order rejection at incoming inspection may occur. I'd like to close off with a couple of case studies that we have here at Epec. The first were two rigid flex part numbers for a power distribution application. Our customer came to us with a requirement of improving the quality and also the reliability of the supply chain, while in turn maintaining the existing price targets. The challenge that we saw from doing our design review was that the supply design did not meet current IPC standards and materials. The solution that we applied, we revised the design to meet the latest IPC standards. We also had an opportunity to utilize more cost-effective materials. We had a number of technical sessions with both the end user and the contract manufacturer to inform them of the benefits. And ultimately, we were awarded both part numbers, and the end user is implementing the correct design standards in their current and new part numbers. An additional case study, and this one was for a medical care communication system. We were allowed to be involved in the design of this part right from its inception, and we developed a very good technical communication and assisted the product designer and the production team in achieving their design and production requirements. The specific challenge, the end customer and design house lacked hands-on experience in all areas of rigid flex design, be it either Gerber layout, material selection, or manufacturing specs. The solution, we worked closely with their design team and the contract manufacturer to develop the design and to ensure its manufacturability. We utilized our in-house capabilities for Gerber layout. In this case, it was an impedance control design, and provided a complete materials and specifications package to the end customer and the CM for their review and approval. Ultimately, we achieved a 100% successful introduction, which passed all tests and qualifications. And the part number is currently running in volume, and as a byproduct, there were two additional part numbers which Epec won. And that covers the content of our introduction. Again, I appreciate your attendance this afternoon. And at this point, I will switch it back over to Ed for our closing. Thank you, everyone.
Paul, thanks again. We appreciate you taking the time. As many of you know, we do more than just flex and rigid flex printed circuit boards. But the reason that this particular slide is here is because many of our other products use flexible and rigid flex printed circuit boards. Specifically, if you look at membrane switches, many of the higher reliability membrane switch actually uses a flex PCB versus a carbon printed circuit in order for higher reliability. And then our heaters and sensors business, between flexible silicone rubber heaters and cap-down heaters, many of those use print and etch technology that are on polyamide flexible materials. So again, we thank you for taking the time. We look forward to you joining us on our future webinars. This again will be sent out to you, and if you have any specific questions, we will be happy to answer directly towards you. And we're, again, always available, and Paul's always available for phone conferences, for Skype conferences, and for in-person visits. So again, thank you all very much. We appreciate it, and we look forward to hopefully seeing you on of our webinars. Thanks again.